All right, I have to say welcome back for those of you on YouTube. Also, if you're on YouTube, don't forget to hit like and subscribe. I think I'm supposed to say that. The more of you that do that, the more I might actually come out with merch, and that merch will be just amazing. Limited edition, let's put it that way. Probably pretty terrible. It might even be my used clothes. I don't know. We'll see. That being said, couple things about the schedule coming up. I sent this email yesterday, but I want to make everybody aware of it. Today is the 17th. I'm giving a lecture. Hi, nice to see you. But that's the last lecture I'll have for a week and a half. I am heading to a conference tomorrow, and I will not have a lecture. I call it live lecture on the 19th. Then Tuesday and Thursday of next week, I'll also be out of the country even for another conference, so I won't be giving lectures there either. There will be office hours tomorrow for me between 8:30 and 10:30. Vladimir's still going to have his between 9 and 10, so you can take your pick as to who you'd like to talk to. I won't be offended if you pick Vladimir. In fact, you might make a better choice by picking Vladimir. Let's just be real. Next week, there will be no office hours for me, but Vladimir, I think you're still going to have yours. And that's important because homework 2 is about to come out. Actually, it should have come out already. It's basically a homework from intermediate statistics, if you took that class. But I'm going to get you to do Bayesian methods with it. It's basically a Bayesian linear model. And then formative assessment 4. Normally our formative assessments are due every Monday, but because we're not having class next week, that one's going to be a little bit longer. It's like 2 weeks worth of formative assessment, and it'll be due on the 30th, so the following Monday. So just a heads up for all that. Any questions for me about anything I just mentioned? No questions. Love it. All right, moving forward. Let's take a look at the homework. The homework that I have assigned, just to give you the heads up for, it should be the case that after today you might be able to build this homework all together. But basically, there's a story about playing Scrabble. Story ripped from the headlines of my life. You know, there's this show, I think my spouse likes to watch it, Law and Order, where they try to make a headline, a fiction story about headlines about law, crime, and punishment, Law and Order, stuff like that. This is homeworks that you see from Lisa Hoffman or me are usually about our life, and so this is us playing Words with Friends or Scrabble way back in the day. So basically, the idea is I'm looking for you to do a linear model where you're predicting the score of the test itself, the score of the Scrabble result. And basically, when you run this linear model, we're going to come up with what we do today. The idea will be to answer a set of questions about it. These questions are questions that you might have in a regular linear regression class, but to use your Bayesian estimates to answer those as you go through. The homework itself, I would advise that you start early, particularly because if you've never used Stan before, it will be a challenge to get things to compile. But that is where I'm leaving the country, so I drop this homework on you and I tell you good luck, and Vladimir, good luck to you too. But no, I don't mean that. But do start it early and see if you can do as much as you can. Because I made it due on October 4th, which is, I think, 3 weeks. A little over 2 weeks, pardon me. 2.5 weeks from now. So you should be able to have a chance for that. All right. Any questions? Didn't do a good job there, but that's okay. The other thing I'll note, if you are really interested in seeing what I've taught before, if you go to my teaching section of my website and you scroll down to my recent courses, there's the class that we taught here back in 2022, and in that class there's this basically the same material. I haven't really updated things. I've tried to clear up some of the errors that are in my slides to varying degrees of success. But the idea being that if you wanted to look at perhaps things that are going on or coming up, you're welcome to go ahead in that class and see last year's lectures as well too. But it's not required. I will be giving those lectures when I get back as well. All right. So let's dive in. Remember where we left off last time? Last time we were getting into Stan and MCMC. Changed your life forever, maybe. Keep saying that. If I say it enough, it's got to be true. At least that's what I think. We'll find out. But the idea being that we talked about chain convergence. We talked about what a Markov chain looks like. We talked about good convergence versus bad convergence. Like this is a bad Markov chain here. And then we left off here where we're talking about MCMC options, right? And so this is the idea. If convergence is assessed by, remember the R hat statistic, which is a ratio of between chain variance to within chain variance. We want that statistic to be 1. So that was the motivation for running multiple chains. I prefer 4 because that estimate of between chain variance is a little bit better the more chains you run. But again, it may be overkill. There are those who disagree, and that's great to disagree. There is a warm-up period in every chain. Remember, the Markov chain starts with a guess at the parameter that's really terrible, and then through successive iterations, the parameters are supposed to, in the long run, get closer to the center of their posterior distribution, where we're sampling from. That means that we need a warm-up period at the beginning of our chain. That warm-up period is difficult to troubleshoot, and you sort of get into it when you start to run models, but if you somehow run a chain and it doesn't converge, the next step is to lengthen the number of iterations in warm-up or burn-in. Also, the last part of the chain, after you get past the warm-up period, is the sampling period. You can also increase the number of iterations there. Depending on the type of statistics you're looking to summarize, you may want a really long sampling period, or or you may get along with a short period as well too. So that is the idea for MCMC options. Any questions or anything you'd like me to review about last time before I move forward? Great. So this is the picture from the beginning of this lecture. Now that you've gone through what a Markov chain looks like, what do you think of these time series? Now, would you say those are converged? Remember, we're looking for sampling like just a big caterpillar, looking like a caterpillar here, or a, dare I say, a seismograph in an earthquake? I probably shouldn't say that. Those of you who are from the Pacific Rim or other places in the world may not appreciate that. But generally speaking, we're looking for sampling that's very stable. There's not trends in the sample, right? And this appears to be stable. The lack of trend, right here, if you look here, this is a trend. Each of these parameters are still moving, right? This is bad convergence. Remember, this is me using 10 for a warm-up period. And then this is the first 100 iterations after that. You can see these parameters are trending toward what will become the center of the distribution. Once they get there, though, they stay, and they're flat. So we want to see that flat. And then, of course, we can take all of those. This right here is 10,000 iterations times 4 chains, right? So this is the order in which they came in. And then we can disaggregate the order and just come up with a very smooth histogram to get a shape of the posterior distribution for each of these parameters. So now we've assessed convergence. Or actually, we haven't. We've used our eyes and said, hey, these look converged. Let's go to the numbers and describe our chains. This is sort of the end point of the Bayesian analysis that you get to. And I'm doing this, again, with just basic model. We only have 2 parameters here, an intercept, which represents a sample mean, and standard deviation. In this case, in an empty model, it represents the sample standard deviation. But this process plays out for the simple model, and it plays out for the most complex model. So whether we have 2 parameters or we have 2,000, we do the same thing, right? We look at convergence, and we describe, if things are converged, then we go and describe what that posterior distribution is telling us. So now, assessing our chains. In Stan, once you've sampled, once you've done the sampling process, once you've taken your data in R, sent it to Stan, Stan did the work, it built an executable, it ran the executable, it sends back data. The object that it sends back data to, in this case, what I call model00.samples, you can assess its summary by putting a $sign and the word summary with an open and closed parenthesis. And for those of you who aren't familiar with the R6 object, this is a function that's embedded in the object itself. So summary is applying to the object. Whereas normally, for instance, in a linear model, you may have a, there, I can show you the linear model code here. We may create a linear model and call it an object, and we have to use that summary function on the object. In the R6 object, the function is built in. So that's just a little bit of a weirdness to it. But in the summary, you see this output. You end up having a data frame, it lists the various numbers of parameters that will display on the screen. The LP, again, is the log posterior density. This is assessing the chain of the model of the posterior density itself. We rarely look at this for convergence. So this first thing, LP, doesn't matter to us in convergence. We want it to be converged, but there are many cases, particularly of unidentified models, where this will be converged, but different parameters may not be, because those parameters are sort of compensating for each other. So overall, the model is somewhat if the model may be moving toward convergence, but if it's unidentified, some of the parameters may be reflections of each other, and that causes estimation issues. But beta 0, this is our line for it. The posterior mean, so what we do, I mentioned before, actually, let's look at R hat to look at convergence. R hat right here is 1, and that's the number we want to see. So that is telling us that this chain for beta 0 is almost perfectly converged. All evidence suggests it should be. And sigma as well, its R hat is also 1. So that is also 1 to look at. So turns out there's a couple other statistics that we use sometimes to talk about convergence, or to talk about how efficient our chain was. So in our data, when you look at this Markov chain right here, we can talk about something called an autocorrelation. I don't know if you've heard that term before, but basically we have 10,000 draws from the posterior distribution, right? So if you think of our data of having 10,000, and actually I may even just run through this a little bit here with us here. Just a moment, please. I should warn myself about these types of issues. Nope. I'm sorry, just a second here. There is a point to this, I promise. You may not believe it, but that's okay. There will be a point. And oops. Okay. It's compiling a Stan model here. Basically, I want to talk about the concept of autocorrelation. So in a Markov chain, remember that every iteration, each parameter may change. But because parameters are somewhat dependent on each other, right? The value of the sigma parameter actually somewhat depends on the value of beta, right? Because where the likelihood is its peak is depends on where beta is at the time. There may be something called an autocorrelation in our chain itself. So here, if I look at our draws, let's take the beta here. These are our 4 chains. This is a summary of it. Let's do this. Format is all right, and let's do this. There we go. So here, this is our chain object. Here's beta 0, right? And let's see. There's 40,000 elements to it. The first 1,000 of those happen to be a first 10,000 of those is chain 1, for instance. So if I took just the first 10,000, like that, and let's just take a look at that. This is a histogram of that posterior distribution of that first chain. That looks very similar to our regular histogram. If I wanted to go and describe how efficient our chain was, what we could look at is how correlated each draw was with each successive draw. This is called an autocorrelation, right? An autocorrelation, we could define this as basically how correlated draws one iteration apart happen to be. So I could just quickly create a data frame with that. I could call this temp equals cbind, and let's take chain 1 and 2 through 10,000, and then chain, actually, I need 1 through 9,999, and then I need 2 through 10,000. So now I've created the data frame that has each iteration and then each successive iteration's value. And then if I take the correlation of that, this would be called the autocorrelation. So what that tells you is with each successive iteration, every next value of a parameter is correlated at 0.17 with the value before it. And for those of you who've taken a multi-level class before, this is where we have a multi-level concept that comes into mind here. Why this number is important is it describes how many, if we were to look at our chain, in total we ran 10,000 iterations of sampling for 4 chains. We had 40,000 samples drawn, right? So that sounds like a lot, but if the autocorrelation is high, we can define a concept of an effective sample size. Basically, what would the sample size be if the correlation was 0? That describes to us how well our chain, or how well sampled our posterior distribution is. So, whereas beta 0 here, we ran we ran 40,000 iterations. The effective sample size in bulk or in the tail, and I'm blanking on what the difference between these two numbers are, but let's just say it. This is basically saying in bulk across the entire chain, I believe, we have 29,630. It's like we ran 29,639 independent samples from the posterior distribution, right? So sometimes you will see autocorrelation will be a part of the chain that we worry about, because if our model is very complex, we may have a high autocorrelation from iteration to iteration, mainly because it may take a while for the Markov chain to sample the posterior, given how everything is dependent on each other. So what autocorrelation tells us is we could effectively think of our sample size for our chain as being 29,639 independent draws, right? So that comes in handy when you want to talk about summary statistics as well, too. Yes, Vladimir. This is the estimation of the independence. This is how many independent draws effectively we have from the posterior distribution once we factor in the autocorrelation. That's right. So these results over here are based on the 40,000. But if we were to talk about how many independent draws we would have, like how much information do we really have that's not overlapping with other values, we would say we really had 29,000 draws. Now, 29,000 draws is a lot. All right, we have a really good number of draws. This is good. But that number you may want to look at. I've seen that number get down under 100 before. Well, what we're about to do to summarize these statistics will tell you why that's a bad idea. Okay? Other questions? No questions. Okay. So, finally, at the end of the lecture, on slide 37, we can talk about our parameters. Maybe that's just me being verbose, probably. But this is a complicated topic, and I wanted to make sure we are slow enough on this so we get it, because this is foundational for everything else we do. When we've assessed convergence and we think we have a good number of draws in our chain, we can now interpret the results. And for the results, remember, we ran 4 different chains, but if they converged, what we will do is disregard all those samples or which chain they came from and pool them into one big set, right? So in the previous slide, this 29,000 reflects what the autocorrelation impact is over the 40,000 in total. And these numbers are based on 40,000, not within each chain itself, the 10,000. So we're going to pool all those 40,000 samples into one object. And we end up with a plot. We can plot them right here. These are the posterior densities right here for each. Now our goal is to summarize these densities, right? If this is our posterior distribution, what is it telling us? So now it's back to basic statistics, believe it or not, right? The most common type of summary for each parameter that you have is taking the mean of the posterior distribution. The posterior mean has a very special name. It's called expected a posteriori, right? EAP for short. An EAP estimate is a posterior mean, and it literally is the average of 40,000 values. Right? So if I go back to my R code, I have this object here called chain. This was our chain for beta. There's 40,000 values to it. If I wanted to summarize that, the posterior mean is 171.0093, and that should be the result I have here. 171, we lose the decimal place. So literally, it is just the mean of all of our draws, right? The hard part in Bayesian is getting to the draws. Once you have the draws, it becomes basic statistics. We take its mean. That's great, right? Now, there's an important point to this. Actually, there's other values you can see as well, too, right? So, for instance, we have a mean, that's output. We also have a median, that's output, a posterior median, right? That posterior median may be important in the case of, like, for instance, the sigma parameter. This is a skewed distribution, as we would expect for a small sample size for a variance, right? So the mean is pulled towards the tail, where the skewness is headed, and the median is somewhat toward the more the center of mass. And so for sigma, the median is what we might want to use as well too. But here's the important point. The posterior means are different than what we get from a maximum likelihood estimate, right? Think of why that is, just by the name itself. In maximum likelihood, the parameter we find is the parameter that maximizes a likelihood. A maximum of a likelihood is where the peak of the curve happens to be. The posterior mean is where the average of the density happens to be. So just the idea, if these were MLEs, ML, the M part of it, is trying to figure out effectively where the peak value happened to be. Whereas in Bayesian, our mean is what we often use, so the mean may be different. So when you compare Bayesian estimates with maximum likelihood estimates, when you're comparing EAP values with their ML counterparts, you will see differences, particularly when it comes to variances, because the variance tends to have a skewed distribution. So just be aware of that, right? The ML estimates, if we were to talk about them in Bayes, those would be the modal values, right? The peak of the density. And for symmetric densities, the mean and the peak, the mode, are basically the same. But for non-symmetric posterior densities, they're not. And that's often the case with variance estimates. They're not necessarily symmetric. As n goes to infinity, they all become symmetric. They actually all become normally distributed. But we don't always have an infinite n. I hate it when that does that. Questions on what I just mentioned? No questions. How is the pace? Too slow? Too fast? Just right? I got a thumbs up. 2 thumbs up. Thanks for voting. Those of you who think it's too slow didn't vote. Fine. Sorry. Thanks for your kindness. All right. So that describes the center of the distribution, right? So we have a posterior mean as our point estimate. Oftentimes, when someone say, what's your parameter estimate? You give them the EAP value. That's your parameter estimate. But we also need to describe the uncertainty in our posterior estimates as well. So it turns out, just like in basic statistics, if the mean is a measure of central tendency, we often talk next about measures of spread or variation. Standard deviation is our use for that. So it turns out we use the posterior distribution's standard deviation to calculate our posterior standard deviation of our parameters. Now that may sound basic to you, but it turns out this is analogous to our standard error in maximum likelihood, right? Where we get a standard error from, like if you do a linear model, such as the one at the beginning of my slides right here, and we get our linear model values, there we go, this standard error is formed by what we call the asymptotic distribution of our maximum likelihood estimate, right? As n goes to infinity, we know what the distribution should be, and that value tells us the standard error is 9.041. Well, if we wanted to form confidence intervals back in the frequentist world, we'd take, our point estimate, we'd add and subtract, some type of distribution around this. We know it's sort of a t statistic, so we could talk about that. We could build a posterior, like a posterior-like distribution for our parameter. That's ML. But the difference between that and what we're doing in Bayes is in ML, that's all based on assumptions and theory, right? As n goes to infinity, this should happen. For that to be true in ML, we have to have a large enough sample to approximate it, something that we call asymptotic convergence. However, in Bayesian, our posterior distribution may not be asymptotically normal, and that's okay. We can still summarize it. We can still talk about the standard deviation of it being its variance for it. So that's one measure of standard deviation. So if we were to look at our parameter estimates, we know that the posterior standard deviation for beta 0 is 9.44. Ironically, a bit wider than our posterior standard deviation in ML. Anybody want to guess as to why that might be? The answer is Bayesian. We have this. You said that the Bayesian process, the chain, has a lot of sort of uncertainty in it, and so that characterizes it. And I would say it's close, very close. I would actually go this way, and I would say two reasons. Number one, our standard error is actually involved. Our residual standard error is involved in the standard error of our parameter estimate in ML. In fact, we can show that the design matrix, which X, right? We can show that the asymptotic covariance matrix is sigma squared, right? The squared term of this times X transpose X inverse, right? So we can actually define that. And in this linear model sense, it gives us a good sense of it. However, what happens in ML is that sigma squared is sort of falls out, sort of profiled out. Meaning we estimate it and we put in its point value with certainty and we leave it alone. But in Bayesian, we sampled it. And for small sample sizes, our sigma squared has quite a bit of error, quite a bit of uncertainty. And so that uncertainty in sigma squared that we allow in the Bayesian process bleeds over into inflating the standard deviation for our beta 0 parameter, in part. So part of what the issue is that we actually have changed how we estimate the model altogether. We put in sigma squared as a parameter, and rather than substituting its own point estimate, we end up just using its, we allow it to vary. If I had gone back in to this analysis and had fixed sigma squared to be equal to the point estimate that was in ML, so I made it 49.52, it turns out, if I use an uninformed prior, I'll get very close to the same result as ML, right? So JC, you were in part correct in that the error is there, but that part is in ML we just put in sometimes in this is least squares estimates that I'm showing you on the screen here, but the maximal version of this basically profiles out sigma squared, puts in a constant for it rather than allowing it to be estimated. So the other part I sort of mentioned as well too. The other reason why this number may be different than our ML counterpart is our priors. If we tighten our priors, it will shrink. Right? If we make very informative priors, that posterior distribution gets smaller and smaller and smaller. We make very uninformative priors, that posterior distribution gets very, very big itself. Questions? All right. So there's another thing that there's another quantity we may want to use to describe the posterior distribution. And that's the idea of a credible interval. A Bayesian credible interval resembles a confidence interval. Okay? So remember back in basic stats, the idea of a confidence interval? How many of you are TAing intermediate this year? Have you gotten to confidence intervals yet? No, I don't think you have yet, have you? No. But when you get there, what does the confidence interval represent? That's right. The number of times. So if you repeat the experiment over and over and over again, the portion of times that parameter will fall within that window, effectively, right? The Bayesian credible interval describes basically the same concept, but because we're talking about the posterior distribution of the parameter itself, the credible interval tends to be the description we give confidence intervals, which is we're 95% certain the parameter falls in these limits, which is not true in frequentist world. It's if we repeat this experiment over and over again, we would see the parameter in these levels. It's not saying the parameter is, it's just saying this experiment for itself. In the Bayesian confidence interval, the credible interval, we can say literally because the Bayesian credible interval is an interval on the posterior distribution, and that posterior distribution is the distribution of the parameter given the data, right? We can go put an interval on this and say with confidence how likely or what our belief is a parameter will fall within that region. And that is why it's called slightly differently a credible interval. In practice, we tend to treat these very much the same as confidence intervals. They're helpful. But in Bayesian statistics, they take on additional meaning because in Bayesian statistics, we don't often do hypothesis tests, not the traditional way, where we form a null hypothesis. Because hypothesis tests also need to be ideas of posterior. We could, in Bayesian sense, we could come up with a prior probability of the null versus a prior probability alternative. So the idea of hypothesis testing doesn't map entirely onto Bayesian statistics, although again, it's still close. Everything we're doing is close because of asymptotic properties. This credible interval is how we determine whether a parameter is close to zero or not. Because what we can say is, nobody wants to do a hypothesis test on intercept. We rarely ever do that. But if you wanted to, you want to say, is it possible that beta 0 turns out to be, let's say, 0 or some other value that we are interested in? You take a look at the credible interval. In the output here, we have a Q5 to Q95. This is a 90% credible interval. And the value is between 155 and 186. So we're 90% certain beta 0 is between those two values. So because 0 is not in that range, we'd say, yeah, we're not at all certain. We believe that it cannot be 0 because it's not in that range. So credible intervals are yet another way of describing where our posterior distribution center lies. And it turns out there's multiple ways to take an interval. Like in frequentist land, we often talk about confidence intervals. We do, point estimate plus or minus something from the distribution times our standard error, right? Well, in Bayes land, our distribution is not symmetric. So we don't do plus or minus 2 because that would give us a wrong result. So what we have to talk about is drawing in our distribution where the center point of the distribution happens to fall. And there's multiple ways to do that. For instance, I could start a confidence interval very low and have it be asymmetric and put 90% of the curve in where maybe I go between 125 and 180 or something like that. That would also be 80% of the mass of the distribution. But often what we come to is we call a very specific type of credible interval our favored one, which is something called the highest density posterior interval. It is the narrowest range for where the confidence interval could be. So if you look at this distribution, if I were to draw two lines such that 90% of the mass of the distribution was in the center of it, the two lines that were the closest together from that would be what's called the highest density posterior interval. We shorten that to HDPI. Turns out there's ways we can get that. There's a package that I've added into the example. In fact, it is the HD interval package. And using that package and giving it our parameter estimate itself, we end up seeing the credible interval is real close to what the highest density credible interval is very close to what the standard credible interval happens to be for what we do for each of these. It's slightly lower in the variance sense, but that's about it. So credible intervals are confidence intervals in Bayesian. Think of it that way. But because we don't have symmetric distributions, we really could draw a credible interval anywhere. So people describe the highest density posterior interval, highest density credible interval, as that where the two endpoints of it are the closest together. So the center of the distribution is right in the middle of it. Any questions on that concept? Okay. Well, turns out in homework, what I just described, you will be reporting. So when estimates are requested in homework, as you get into our analysis, I'm going to ask you to describe the posterior mean, EAP, the posterior standard deviation, and the 95% highest density posterior interval, which is the upper and lower bound of that as well too. I even give you some choices as to how you model the analysis itself. So what I just described in this, so let me just pause for one moment, take one more drink. Questions on anything about this lecture? It's lasted 3 class periods. Anything I can talk about that'll help you, anything that you're unclear about as we end this one right here. I'm going to switch to the next part of this lecture for the remaining part of class time, but let's pause here for a moment. Thoughts, questions, comments, anything? Okay. I took my drink. I'm ready to move forward. Try not to touch my desk. My floating hands. So this lecture, even though we had a very basic model, is the process for how we use Stan throughout, and how we build a model in Stan, how we set options to run Stan, and how we summarize, check convergence, and then summarize the model when we're done. This same process is what will happen every time you run a model, every Bayes Markov chain model, every MCMC estimate you do, this will follow you. So it is even though very basic model, it is how it works. And it's easier to see basic than it is when you get to more complex. All right, shall we move forward? Let's move forward. So today I listed